I'll talk about mean field methods for computer and communication systems. Perhaps the most intriguing thing is what really the mean field interaction model is. And I will spend some time discussing that. And last, I will talk also about the infinite horizon, the fixed point method, which is not intriguing, but is a place where often this technology is misused. So I'll try to talk about why it's misused and how we can avoid misusing it. So mean field interaction model is primarily a simplification of a system which we model with a Markov chain. The terminology here too might be a bit misleading because it's used in physics, like all the good things we're doing, they come from physics. Where the model is called sometimes interacting particle systems. And there are two keywords that are associated in physics with mean field. One is independence, and the second is approximation methods. I'll talk about those. Mean field is a misnomer. It's like slow start in TCP. Mean field typically would mean that you summarize a complex interaction by just its mean. And that's not what it is. It's in fact summarizing a complex interaction with its distribution, which is much richer than the mean. But of course, we can view the distribution as the mean of a sample if we want to argue in that direction. Why do we care about this in the field where we model artifacts created by humans in computer, communication, or electrical systems? Well, there's similarity with the models of physics, but there's also differences. The similarities is when we have many objects and somehow the system is distributed. So this has been applied to communication protocol, game theory, and other examples that I will give. Perhaps the major difference with what people do in physics is that in our field, the model, we don't have as much time to study a model as people do in physics. Usually we study a model because we want to study an artifact that perhaps we are creating also. So in the same PhD, we invent a system, we prototype it, and we analyze it. Whereas in physics, the models usually has been put on the table, hard to understand, and perhaps 20 years later, somebody will understand. Chances are, if your system is not analyzed today, it will not be analyzed in 20 years. So we need more reusable results to be able to make use of that. That's also one of the themes I will discover today. One way to make results more usable is to have a factory of models, a general way to describe how we can think of a model. And here is perhaps the most general one, or not the most general one, but ones that we can use in practice without working too much. I'm assuming here time is discrete. This is not really a limitation, but this is just to simplify the story today. We assume we have n objects. They're called particles in other settings. In our environment, we often prefer to call them objects. And n is large. If we have 2 or 3 objects, probably that doesn't work. Now, how large is, as usual in statistics, it depends on many things, a few hundreds perhaps. And the key thing is that every object has a state, such that the collection of states of all objects is Markov. So I put a capital N in a subscript here. It means when the total population is N. So I must be able to describe the state of an object. And my complete system is the collective state of all the objects. And the key assumption, which is this one, is that objects are observable only through their state. It looks like an innocuous assumption, but it really means that if I am simulating the system, there's nothing else I need in my simulation than everything that is described here in this state description. Key quantity that we will derive from this is called the occupancy measure. It's when everything is discrete, can be interpreted very simply by saying at time t, of course, here, the state will evolve with time. So at time t, I can define or describe the distribution of object states, which if the state of objects is in a finite set, it simply means how many objects, or what is the proportion of objects that are in every possible state. Then if we assume that this is Markov, then it can easily be seen that that is also Markov because of this key property here. So in other words, and that's the key step we make here, in order to understand this system, all we need to do is understand the dynamic of this. But this is only half of the story. What we will see is that by understanding the dynamic of this, we are able to recreate whatever we want of this one here. So we're able to go back and forth, and this is the key thing of this theory. It has received several names, but I think the one that has stabilized now is to call it the mean-field interaction model. That's a term that was coined by McDonald in a paper of 2007. This has been applied with this terminology or with variants of this terminology in a large number of papers. I'm just mentioning here a few ones. As you can see, they go from transportation systems to models of HTTP, many models of data and communication systems. I interviewed, when I started this research, I had a concrete problem of that nature, and I interviewed Armand Makowski, who was one of the authors there, and I wanted to understand how his analysis of the Infocom paper that he published at Infocom for the first time in 2003 would be reusable to my system. And his statement was, oh, it was a pain. I will never do it again, showing that there is convergence to mean field. What are all the equations? And then somehow I sort of stopped and said, okay, let's do that when I have more time. But still, it's surprising that there's such a large number of applications of it. And each application originally was like a handmade application of a theory that did not exist. So what I will present today is the theory, at least for the simple cases, and how we can avoid having to redo all of those works. I will explain the theory on a very simple example. The example is too simple to be really attractive, but that's one on which we can do all the maths almost manually. It is too simple because there's only 3 states for a given object. Usually we are interested in much more states, and as I will mention again a bit later, one of the key features of this formalism, which is often misunderstood, one of the key features is that the state can be anything. A state can be a location, it can be a class, so you can model objects that do not have to be homogeneous. Usually mean field in the roots examples are very homogeneous, but it doesn't have to. So I will show a few examples where that does not have to be. So here, this is a bad example if you want, because things are fairly homogeneous. It's an example that was inspired by some work I did with Georgios Theodorakopoulos on 2-step malware propagation, where we assumed here a simplification of a virus infection where the virus sleeps and hides. So we can model this by saying there are nodes that are either susceptible when they're not infected, or dormant when they're infected, but the virus is in a special state where it's not really visible. Your system works completely well. And A, when it is active, when it is doing its job, which consists in stealing or killing stuff. I can model this by assuming that to simplify this example, but I will stress later that this is not a limitation, that nodes meet pairwise. So nodes can involve, can change their state, or they can change their state in isolation or by meeting other nodes. Typically, this is what happens in an infection. The state of one node is one of those 3 values, so I call them SAD. There are 3 states, therefore. The occupancy measure is, I call it S of t, D of t, A of t, is the proportion of nodes that are in state S, D, or A. And those are numbers between 0 and 1 that sum to 1. And let's assume for this specific model that I have interactions that are described in this way. This is using the formalism of chemical reactions. In fact, the framework of chemical reactions, the dynamics of chemical reactions, when you write differential equations for the dynamics of a chemical reaction, you're in fact applying some variant of the theory that I'm presenting today. Or to be more precise, the theory I'm presenting today is largely inspired by what of people in this chemical or biochemical setting. I write, for example, D plus D gives A plus A. That means a meeting can occur when a node that in state D meets a node that in state D, and both become nodes that are in state A. This is because the logic of the infection makes that possible. And then I can have a number of other transitions. In Markov chain language, we would call this a transition. An A can spontaneously become an S. Of course, it's probably not spontaneous, but that means that something that is active becomes susceptible. It's been cured by applying a patch, for example. And there can be recruitment by dormant, which is the main feature of this activation. When nodes are infected, but not visibly infected, this is where they will most actively recruit and infect others. And they will become visible only when enough of them meet each other. So this is one toy example, if you want, that is a simplification of systems that we had found in practice. What can I do with that? Of course, I can do more fancy things than the one I'm showing here, but let's come back to very simple things to understand what is the mechanic of the mean field approximation. I can do a simulation with a finite population of nodes. So here I have a few hundreds of nodes, and I can simulate the proportion of nodes. For example, d of t is the proportion of nodes from some initial combination, initial distribution of states of how many nodes are in each stage. And I can also zoom on 3 specific nodes that I call nodes 1, 2, 3. And see what happens to them. And I'm showing here the dynamic. Of course, the dynamic is not very exciting because there are only 3 possible states. So we see that nodes that are, for example, susceptible, after some time they can become dormant, then infected, then cured again, etc. And the process can go on. I can do that for all the n nodes that I have, and I have a complete simulation if I know, of course, all the details of the rates of the probability that meeting occur at every time slot and the probability that infections are successful. So this is a simulation for a few hundreds, I said 1,000 nodes. That's one thing we can do. I can also plot what is called sometimes the phase diagram. Instead of plotting the S and D separately, I can plot the distribution M of t, the occupancy measure, in the simplex. So I have d of t on the x-axis. Y of t is A, the proportion of A nodes. And since the sum of this is 1, the third component is not shown, is the distance to the diagonal. So I stay somewhere in this triangle. And this is another view of what I have simulated. I start with some initial condition by saying I draw randomly a number of nodes. And perhaps I can impose the number, the proportion. Here, this is what I did. This blue circle is the initial condition. If I simulate the system, I will see that the population evolves. And if I start from here, we'll get there. For this, we will see that there's a red cross where it seems that all nodes are converging to. Well, this going to the global population from the initial nodes and back, this is the whole story of mean field. What do we see on this? Well, we see that we have a random system. The occupancy measure, the green trajectory is random. If I would redo the simulation, I would find a slightly different thing. But it has some qualitative features that are not random. And it looks like there is a pattern that we can see here. For whatever initial condition, we will end up approaching the red node, and we will do that by taking an excursion to the right. So this is what qualitatively we can see on the dynamic. That's the kind of thing that's very difficult to capture when we use the classical Markov chain modeling. If I give you a Markov chain model of something, what is the thing that most performance analysts will do? What is the question they will ask? Well, probably they will ask, what is the stationary distribution? Does it have a stationary regime? What is a stationary distribution? Here, the stationary distribution will be something around the red cross. But you will not see all that stuff. We will see it if we take another approximation, which is the mean field limit. I want to mention, I will continue the rest of the talk on this example, but I want to mention that this example is much too simple compared to what we can do with it. Here is the original example that motivated by my research was an example where Armand Makovsky and Tina Korn were modeling TCP and ECN. Here, the time is discrete. An object is a TCP connection. The state of an object is the size of its window. And there is also a global state here, which we can view as a specific object that has one special property, which is the queue length at the router here. We also studied work inspired by PhD thesis of Sonia, and the reputation system can also be modeled with a mean field model, but this we understood much later how to do it, in fact this year only. I mentioned that the attribute of an object can represent whatever qualitative feature we want to show. Here is an example which we apply to a geographical feature. Here the objects are taxi cabs, and we want to see how much time it takes for a taxi to gain information that was learned in the heart of a city, and how much time it takes to propagate by ad hoc dissemination in an area where things are certainly not homogeneous, because there is a highway structure that very strongly structures the space, so it's not a random movement. And we found that if we apply this, then the class of an object is, in this case, it was the age of the latest piece of information that it has, so it's a real number, but it can be also discretized, so a positive integer, for example, or a real number, as we wish. And if we just take this as object, we have a homogeneous system where we assume nodes meet regardless of anything except perhaps their age. If we do that and we try to map what the mean field model predicts to what simulation give, we find a QQ plot, which is supposed to be a straight line if the distributions are the same, which is not correct. But with 16 classes that correspond to 15 very coarse discretization of the area plus 1, which is the outside, we find a very good match. And this is something we've seen very often. A little state very often is sufficient to make very good match. And now what do you have with this? What's the benefit? Well, you will have, in a case like this, an explicit formula for the distribution of state, which is here age of object, based on their location and based on time. So you can see, in particular, you can ask questions. What is with 95% probability, how much time does it take to propagate an information using ad hoc dissemination here? Once we have recognized what are the kind of systems or the kind of models we can apply to our systems that would fit with this framework, the question is, what can we do with it? Well, we can do large N asymptotics with finite horizon, or with infinite horizon, the famous stationary thing that we do for all of our Markov models. And one of the issues is when this is valid. And this is practically always valid, but not always. It depends on something that is called a scaling law, and also some structural properties of the system that I will describe now. And this is the difficult part. If you have a specific model, that might be very difficult. It may take a whole PhD to prove that when n gets large, we can approximate our system with a mean field limit. But what I will show here is how you can avoid making a PhD on that. So the topic is when we can have convergence to something which is an ordinary differential equation. The key thing, which is perhaps an act of faith, is to recognize that what we will do when we apply mean field limit is we will not simulate or understand our initial system, but we will believe that our system is one in a class of many systems that is parameterized with a size parameter n, and what we will get is what happens to our system when n is large. So this is a classical asymptotic evaluation that we will do. Of course, that leaves aside a number of practical problems. If in reality you have only one system, you don't have a moving n, but a fixed n, is n large? This answer I will not be able to give today, so all we will see is what is the limit of our system when n gets large. To get a limit, we need some scaling law, and the key quantity for the scaling law is what we call the intensity, which is the expected number of transitions per object per time slot. So remember, an object has a state, and the state of the object changes, and if there's a large population, there are many changes. But we need to take both a decision on what we call a time slot and an intensity such that the intensity I of n will essentially vanish. So this is the key quantity, which has to do with fixing the time slot. At which time scale are we observing the system? So this is the number of transitions per object per time unit. If there are n objects in total, the total expected of transition you will see per time slot is n times this. And the mean field limit occurs when we rescale time by this. So in other words, instead of considering the initial system with n objects, we consider the system at time t divided by this intensity. And this will be particularly interesting if the intensity remains constant when n gets large. In that case, we have a rescale system that if the original one is in discrete time, then the limit one is also in discrete time. That's the easiest to describe, but it's not the easiest to compute with. So what I will describe today is another case where the limit is in 1 over n, or more generally, where it vanishes. Whether it vanishes like 1 over n, or 1 over log n, or 1 over square root of n is immaterial. It will not change here. But this is what I will focus on today. So it means essentially, I assume that my time slot is 1 over n. When I have n objects, I assume that I observe the system with the time resolution of 1 over n. If I have 1,000 objects, roughly speaking, my time slot is 1 over 1,000. And the assumption is that I need to be able to compute the probability that an object does a transition per time unit. We will see very general conditions for this convergence. And the key result will always be that once I have rescaled my system like this, then I will have something that becomes deterministic. So in some sense, but this is only 50% of the story, we are doing away with probabilities. We're replacing a stochastic system by a fluid one. If it would be only this, it would not be very exciting because we would get only a first-order analysis. What we will see in a minute is that it is possible to get back from the fluid limit here and still say something, even for a finite n, about the stochastic behavior of one object. This is this duality between the collective behavior and the behavior of one object. Or to put it in a different wording, we can view the mean field technique as saying I replace the collectivity by something that is non-random because there's so many objects, but what happens to one or a few specific objects continues to be random, and I'm able to analyze it in a way that is much simpler now. If the state space is finite, which is the example I will show in detail in this example, then the limiting object is simply a differential equation. So something that's very simple, both intellectually, once we accept Leibniz formalism for differentials, and most importantly, numerically, because there are well-defined ways to get around all the difficult cases, so we can easily solve ODEs. We're not talking of partial different equations, but ordinary differential equations. For example, this is the thing we've seen a minute ago. If I simulate my population of 1,000 objects that can be infected, I obtain this. If I write the mean field limit, I will obtain an ODE that I can solve numerically, and I will see that if I take this as initial condition, this is what the ODE will give. And of course, the two are very close, but the thing is it's much easier to study an ODE, and in particular numerically, and it's sometimes, as we will see, we can get even qualitative behavior that will tell us a lot of things that are only approximately true for our system, but are much easier to understand. What are the sufficient conditions for convergence? Well, one typical condition is given here. For example, assume intensity is 1 over n. Well, it means that by the definition of intensity, that means if I have a collection of objects, n objects, during one time slot, the probability that the specific object does a transition is order of 1 over n. It's not equal to 1 over n, but it's order of 1 over n. Another way to put it is to say during one time slot, it will not be the case that all objects do a transition together. So the transitions are, if I look with a time granularity that's small enough, for example, if the real process that I'm mimicking here is a continuous time process, the probability that several objects do a transition at the same time is very small. So that in the limit, the probability that several events occur at the same time that are not coordinated events is 0. So in that sense, this assumption is meaningful. Now, technically, once I have written my model, there are technical conditions that are sufficient. For example, the most sophisticated one is this one. It says that if I call Wn of k the number of objects that can do a transition in a discrete time slot, then, so this is a random number. Transitions of different kinds can occur in an object. In our case, for example, the infection, there can be 0, 1, or 2 objects that do a transition because the meetings are only pairwise. I could have meetings that involve a number of nodes that is log n, for example, in which case the number could be order of log n. So I have a random number, and what I assume is that the second moment of this random number decays fast enough with is upper bounded by some beta, such that this condition is true. And in particular, this is sufficient if this is upper bounded, if beta of n is a constant. If the second moment is upper bounded, whatever the population size, by some constant, 2, 10, 1,000, because then if I of n goes to 0, then the product will go to infinity. So in particular, if I have any interaction where the interaction might be complex, but the number of objects that do an interaction in a given, when something happens, is upper bounded by a hard limit, then I certainly fit in the conditions where there will be convergence. It could even be worse. It could be bounded by log n. Anything that grows less fast than n, for example, would be sufficient to provide a mean field limit. There are other mean field limit scaling. I will not mention them, but I'll give pointers in the paper. So for example, if we look at the small example with n objects that have 3 states, the number of transitions per time step is bounded by 2. Therefore, our results apply. There is convergence to a mean field limit. How do we get the mean field limit? Well, the mean field limit is obtained by computing what we call the drift, which I will describe in a minute. And at the end, what we get is this. So this is the mean field limit of this object. Those are the derivative with respect to time of the quantities that are the proportion of objects that are in each state, which for the original system are random, but we replace them by something which is now deterministic. So we have usually a nonlinear ordinary differential equation, but an ODE. The mean field limit, perhaps the most interesting thing is how to know how to formulate it, because once by inspection, we know whether there is a chance that our system converges to a mean field limit, and the key thing is how many objects can do a transition in a time slot. Once I have that, then the second thing to do is to simply compute the right-hand side of the ordinary differential equation. And this right-hand side is what is called for Markov processes the drift, which is the expectation of the change in the population vector per time unit. One way to describe it is particularly simple. If we have described our system in the language of chemical reactions, remember I was saying, for example, 2D can meet and become 2A's. Then I can describe that by 2 things. First, what in biochemistry is called the effect on the population. When such a thing occurs, what happens to the population where there are 2Ds that have become 2A, so there is -2 in the D population and +2 in the A population. So there is a delta vector, which is -2 + 2. That's in the total population. Now, if my DAS is not the total population, but the frequency, the percentage of the population, I divide by 1/n. So this is the effect of this. Then the other thing I need is to know what is the probability that such a thing happens. Well, this probability is given by your assumptions on the model. For example, here, the probabilities might be proportional to one population and proportional to a saturating function of another population here. Or here, it's proportional to simply the 2 populations and a given rate. So we assume here a complete homogeneous mixing. So the probability is that 2 the objects meet is constant. So if I'm able to do this for each of the reaction, then I simply mechanically can multiply the probability of transition by the effect, and I obtain something that will be in 1 over n. If it is not in 1 over n, it means my intensity was not 1 over n. And then if I rescale by the intensity, I will obtain the limit, which in this case, here is exactly the drift we obtain. When we take the limit, this is exactly how we get it. So this is painful to write, but this is completely automatic. So the only creative thing is to describe the rates and the effect. The effects are usually trivial to do. The rates require some beliefs about your system. Once you have done this, but this is the only place where you have something to be invented and possibly to be criticized. All the rest is completely automatic. In fact, some master students have done some software called TCED. There are many other software that does it, that will take a formalism where you write this, and it will write the MATLAB code for the ODE, the LaTeX code for writing the equation, and the simulus. So that is completely automatic, so you should not spend much intellectual CPUs on it. This, what I described is the simple case, and in fact, mean field theory is split between simple and very hard. So the simple case is when the state space of an object is finite, and in that case, the theory that I'm describing today applies. So all you need is by inspection to know whether your system fits in the framework, and if so, chances are that you can mechanically write the equations. Which equation will you get? I don't know, and that's the beauty of this theory. At the end, you will obtain an ordinary differential equation, and every nonlinear ordinary differential equation is a story of its own. But the key thing is you will be able to study what this equation tells you, and it will tell you a lot of things about your system. And if you're lucky, you will have a beautiful equation that you can associate your name with. When the state space is more general, then we go from simple to very hard. So, for example, I mentioned the age of gossip model, where what we were modeling is how old is the information that a taxi has. If we model this as a discrete number, then it's trivial. It fits in that framework. If we model it as a continuous number, a real floating point number, which is just a view of mind because it exists as much as the other, we can criticize one or the other, then we are in something which is much, much more difficult, and showing whether there is convergence or not can become extremely difficult. In that case, it works, but then it was a PhD to show that it does converge. We did similarly for a very, very simplified model of a subset of one aspect of Sonia's reputation model, and it took, we can say, almost 8 years to prove that there is convergence to mean field of that one. So there is like a binary thing. If we really want to have models that are not in the discrete world, there will be some complexity. Perhaps there are general results. Carl Graham, who is one co-author of this paper, has some such general results, but they are still very partial. So take-home message is try to describe your system with discrete state space. Time can be continuous or discrete. That doesn't make the thing easier or more complicated. But the state space should be discrete to keep things simple. If you're lucky and the thing is not discrete, you can have a nice paper. Now the question is whether that tells us really more on our system. At this stage, I've completed the first part of the story, which is trying to see what is a classical factory for making mean field models. Now the second step will be what can we do beyond the convergence to a fluid equation. And this is called with various names. One of it, again coined by David McDonald, is called fast simulation. In many other papers, we find the word decoupling assumption. And in physics, people would call it the independence assumption. So this is really dual aspects of mean field, which makes it fascinating. This is, in fact, an original result of Schnittmann in Zurich, who showed this. If I have here Xn, which is a collection of objects, I remove t, and this is intentional. It means Xn is the trajectory of the complete system. So a complicated object, if we want to speak mathematically, but it means the complete simulation that I'm making in my system. Then he introduces the concept of M-chaotic. M-chaotic means that the joint distribution of K objects, so you have this population that is perhaps very large, and then you zoom on a few of them, for example, a few objects in my viral infection system. Then I fix K, and I let N become very large. Then I say that this hypothetical system satisfies this M-chaoticity assumption if, when N gets large, it is as if K objects would be independent. And here it's the independent, the complete trajectory, not just the state at one point in time t. This is one definition. So in some sense, because there are many objects, if I look at you and me, our states are evolving independently of each other. Of course, they're not independent of the collectivity. If the collectivity is in a given state, then we will be influenced by that state. But whether you individually are doing this or that will not influence me. It will influence, perhaps, if millions of you are doing this, it will influence the collectivity, and the collectivity will influence me. So this is exactly what is happening. And then we have this result of duality that says that a sequence of objects has this property that when we zoom on a small number of them, they become independent, even though the collective thing is not an IID sequence. This is equivalent to saying the following thing. The occupancy measure, which is defined over much in the way we said a minute ago, becomes deterministic when n gets to infinity. So in other words, the distribution of objects, which is a random thing. If I do, again, another simulation of my infection scenario, I will find slightly different green curves. But if the green curve tends to become deterministic, it is equivalent to saying that there is independence. In other words, convergence to a fluid limit for the occupancy measure is equivalent to saying that 2 or 3 or 5 or 10 objects are asymptotically independent when the population gets large. One or the other is independent. That's a general result that Schnittmann proved. Well, in our setting, or in physics, it's called sometimes propagation of chaos. Chaos being independent as being assumed as independent. In the papers that we publish on analyzing the performance of a protocol or of a database system, this has another term. Usually people call it the decoupling assumption. This is a good example, is Bianchi's paper on the performance of the Wi-Fi protocol, where I assume I have a number of nodes that are trying to access the medium. They can be collided, repeating, etc. And then the thing becomes very hard to study. I don't know how to do it. Then I will put on the table a simplifying assumption, the killer assumption, in fact, which is called the decoupling assumption. I assume that the state of the retransmission state of one node is independent of the guys that are around it. And so that's invariably what we do. When we can't analyze a thing, then we put somewhere an independence assumption. If we do it too trivially, it will give a bad analysis. If we do it smartly, it will make an analysis that works. And essentially, this is what Bianchi did. He did it smartly. So this assumption is called, in physics, the mean field approximation. In fact, when you read papers in physics, they mean independence. Particles are evolving independently. As opposed to convergence to a fluid limit. And as I will try to convince you today, this is in fact the same as a fast simulation result. Let's see on an example what it means. Remember, when we take a small example, we saw that, at least for 2 cases, and I ask you to believe me, that for this parameter set, it always converges to the red cross here. Now, what can I say when and there is convergence to mean field. Therefore, I can say that if I look at 2 objects that have tagged at time 0, I'm interested in node M and N, perhaps my node and Sonia's node. Then I would like to know what is the probability that at time t, it is in the active state. So it's infective and active. Then the answer is, first I will need to rescale. I study this thing here, which is an ODE. And then I will find at time, for example, if I'm interested at time t equal 10,000, I will simulate here the argument here of I will need to find T over N equal to 10,000. So I will simulate this, rescale, simulate in real time this, rescale to find the corresponding number of steps, and then the answer will be the probability that my object in my initial simulation is in this state is approximately the x coordinate of this point here. In particular, if time is large enough, so if I am in the stationary regime, we see that whatever we start from, we will end up at the red cross, at least for the mean field limit. And the red cross has the property that it x coordinate, so A, sorry, was the y coordinate. The y coordinate is 0, 6, approximately. The x coordinate is 0, 3. So that means I can say, if I simulate the system and I run it long enough, I should find that the probability that a node is dormant is about 30%. So my node has a probability 30% of being dormant, and there will be approximately 30% of the nodes that are dormant. Those two interpretations are exactly what the mean field limit is about. So we see that the M of t, the blue line, we can view it as an approximation for the occupancy measure, the proportion of nodes that are in a given state, but also the probability for a given node to be in a given state. This can be used to do what David McDonald calls fast simulation. Assume now I want to simulate the state of a node, but starting from some initial condition. For example, I start from a node, which I call here node 3, which is in this state 0, 0. That means the state of a node is dormant, active, or susceptible. And being here, that means it is susceptible. So its third coordinate is equal to 1. Am I doing poorly? Yeah. Oh, my God. I think I should rescale time, can't we? Then if I do this here, I can solve the same ODE as we had for the mean field limit, but starting from initial conditions that are different. I start from initial condition where I have a distribution of probability concentrated on this. If I do this, I will find this curve here that, of course, converges to the same thing, but will give me the probability that at a given time, for example, the node is in a given state. And we will see that before reaching stationary regime, any node will do an excursion that is more or less large towards a certain state. So we can ask questions like, what's the probability that before getting into that state, a node has been infected or dormant, for example. So this, what is called here the decoupling assumption, is essentially saying that the evolution of one object is as if everything would be independent. That's Schnittmann's result, and that's what I've illustrated here. However, there is a catch to that. If I want to study, for example, what is this stationary behavior, what would you do? Well, you can study this and study the Markov chain. It will have many, many states, so you can do it if n is small. If n is large, what you can do is study the stationary behavior of this. What is the stationary behavior of an ODE? Well, very often, if you ask people, particularly in physics, they will say, well, let's do that. The ODE is dm over dt is a function of m, linear, that's the right-hand side of my ODE. To find the stationary points, I put the right-hand side to 0, because if it converges, this will... If I do this, I will find the red point. So that works well. And I can say it seems to be true. But as we will see, in general, it is not true. I will skip this. This is exactly what is done in Bianchi's analysis of the performance of Wi-Fi. Here is exactly the same system. I've just changed the value of one probability. It has 5 different probabilities. I've changed one of the values from 0.3 to 0.1, or 0.1 to 0.3. Yeah, from 0.3 to 0.1. And here is what happens to the mean field limit. Well, it converges, but it has a limit cycle. It doesn't converge to a point. And in fact, this is an unstable equilibrium, so you will never see it in practice. If I run the simulation, I will see that there is noise around. This is for a fairly small n, but that qualitatively, this behavior here, which is is also reproduced in my random system. That's exactly a behavior that I will never see if I do the stationary analysis, the classical one of Markov chain. In fact, this system has a periodicity. It has a periodic behavior. The state of infection goes into phases that has a dynamic and a critical time that we can compute by solving the ODE and seeing how much time it takes to do one round here. This is the first thing. But the other embarrassing thing is if I apply the method that I mentioned a minute ago to see what is the stationary regime of that, then I will solve f of m equals 0. If I do this for the system, I find the red cross. F of m equals 0 gives me the red cross. But this is not what our system is doing. For this system, there is an implication. In stationary regime, the nodes are no longer independent. If I ask, for example, if I observe a node that is in state A is on the y-axis. If I observe a given node and the node is in state A, then remember, if we believe, which is true here for this example, the true system will be an approximation of this ODE limit. If I observe somebody that's in state A, then probably it tells me something on where we are on the blue curve, where the total distribution of the population is. Because this population is oscillating. If it oscillates and it's in a phase where lots of people are, where many people are in the A state, if I sample you and you are in the A state, it is more likely that the total population is on the top. It's not certain, but it's not independent. It's more likely that this happens. And if it's more likely that the population is here, it's more likely that the second one, that's Sonia, is also in the A state. So we are coupled. We are no longer independent. So the decoupling assumption, though it holds because we have convergence to mean field and we have Schnittmann's result that says that the state of two nodes are drawn independently, but still we are coupled. So there is a paradox, there's a contradiction. And it would be a pity to leave without solving this paradox. So I'll ask you for 2 minutes of extra time. Where is the catch? Where there is mean field convergence for this example, but the nodes are not asymptotically independent. So this decoupling assumption does not mean that it is legitimate to pretend that nodes are independent. For example, when we analyze the performance of a protocol, we say it's too complicated. Let me assume when a node is in state A, then the other node draws its state independently. Well, it's not true. It should draw its state independently given the state of the population, given m of t. Now, if the population converges to a stationary point that is unique, then, of course, we can forget, because if time is long enough, we know exactly where m of t is. But the message is, well, it's rare to have an ODE that has this behavior, although most of the ones we study in textbooks have this behavior. But if you write a model for a given system, chances are your system will not have a unique point to which all trajectories converge. And if that does not happen, there is no reason to have decoupling assumption in stationary regime. And why this would not happen is because essentially we're saying over any finite horizon, if there is mean field convergence, the state over the time interval 0t are truly independent. Now, if I let t go to infinity, I have two limits, time and n, and in general, this diagram does not commute. There's no reason in general that the limit of t, when t goes to infinity of the limit of n is the limit of n when the limit of t goes to infinity. Except in the case where the ODE has a unique global stable point to which all trajectories converge. In other words, in which case, of course, there continues to be statistical independence. I will skip this. And this happens for example, Bianchi has studied the Wi-Fi protocol in homogeneous setting. If we study it in heterogeneous setting, and this is done by a colleague of Zhong-Wu, who is a colleague of yours here, if we have heterogeneous parameters, then we do find limit cycles, which means that the state of retransmission of objects are, in this case here, no longer independent, but in contrast, they are together correlated by the state of the global system. I will skip this, and I will conclude by saying how we should, if we want to use this method, how we should do it correctly. So first, when I have a complex system, I can write the dynamical systems equations, the ODE, in the transient regime. And then the thing which is perhaps new to the domain of teletraffic and the kind of modeling we like to do, well, we need to study the long-term behavior of an ODE, which people in chemistry have been doing forever. That's their bread and butter. But in our field, this is perhaps new. And if it converges to a unique stationary point, whatever the initial condition, which might be hard to prove, in fact, but might be easy to guess, then there will be asymptotic decoupling. Otherwise, there will not, and this is perhaps the most interesting case. That means my system has some collective behavior, which in nonlinear systems is called an emerging property, that will typically not be obtained by finding the stationary distribution of the Markov chain. The stationary distribution of the Markov chain will tell us where in the limit this thing is spread. For example, in the case we have here, the stationary behavior, if I study the Markov chain, I will find a distribution that is around this line here. But being around this line does not tell me that there is a limit cycle. So I've lost a lot of information. In some sense, the limit, the stationary regime can continue to be dynamic, which is perhaps not usual for the kind of models we had in mind. Voila, and I want just to thank you for your patience for my overtime.